Good morning / good evening, everyone. Welcome to the latest edition of zkStudyClub. Today, we're excited to welcome Srinath Setty from Microsoft Research, and he's going to be telling us about Quarks, quadruple efficient, transparent zkSNARKs. So really excited to have you here, Srinath. Thank you very much for taking the time. And with that, the mic is over to you.
Okay. Thanks, Alex. Thanks for having me. And this talk is about quadruple efficient, transparent zkSNARKs. This is joint work with Jonathan Lee. And first, let's dig into what we call a quark. So first, it's a transparent zkSNARK. So what this means is that there's no toxic waste, and the setup involves, for example, picking a group where the discrete logarithm is hard. So there is no trusted setup involved here. All of you probably know zkSNARK, so it's an argument of knowledge, meaning that it's a protocol between a prover and a verifier. The prover is interested in proving the knowledge of some secret witness, such that some circuit outputs 1 when given the secret witness and some public input X as an input. Second, it's zero knowledge, which means that the proof does not reveal anything about the witness beyond what's implied by the statement. Third, it's non-interactive. The prover just sends a single message to the verifier. Finally, it's succinct. There are two forms of succinctness that are generally considered. One is that the proof is sublinear in the size of the circuit, and the verifier's runtime is also sublinear in the size of the circuit. So now let's look at what we mean by quadruple efficient. And naturally, there are 4 efficiency measures here. For a non-uniform circuit of size n, we require that the prover's time to produce a proof should be a linear number of cryptographic operations. Here, lambda is the security parameter. We also require that the verifier time is logarithmic in the size of the circuit. The proof size is also logarithmic in the size of the circuit. Finally, the verifier's pre-processing time should be linear number of finite field operations in the size of the circuit. Of course, we can desire even shorter proofs, shorter verifier time, but we think even achieving this is pretty challenging in this space. So we are willing to label this as quadruple efficient. So if you look at existing SNARKs among these 4 dimensions, so for example, if we look at the first, what I call first generation transparent SNARKs, this includes schemes like Ligero, Hyrax, Stark, Bulletproofs, and Aurora. Here, these schemes achieve a succinct verifier, meaning that the time to verify a proof is sublinear or logarithmic in the size of the computation, only for structured computations. For example, Hyrax requires data parallel circuits. Stark requires a sequence of subcircuits, a circuit that's expressed as a sequence of subcircuits, and each subcircuit should be identical. And the remaining systems like Ligero, Bulletproofs, and Aurora achieve sublinear verifier only if you're verifying a collection of circuits with the same structure at the same time. Otherwise, they all require linear time verification time. Then there is the second, what I call a second generation of transparent SNARKs. These schemes achieve a succinct verifier even for computations that have no structure. For example, if you give a non-uniform computation that's completely arbitrary, they can still achieve a sublinear verifier. One core technique in all of these schemes is that they introduce a pre-processing step for the verifier, where the verifier looks at the description of the circuit and creates some encoding or a commitment to the description of the circuit. And then it uses this at some point later when verifying a proof, so it can achieve sublinear verification time. So if you actually take a look at this transparent ZK, the second generation of these transparent zkSNARKs among the 4 dimensions that I mentioned earlier. So for example, if you look at the prover time, Spartan actually meets the requirement of a linear number of cryptographic operations, both asymptotically and concretely. And in terms of proof sizes, supersonic meets our requirement both asymptotically and concretely. On the verifier time side, supersonic meets this asymptotically. It has a logarithmic verifier, but it's concretely very expensive. So on the pre-processing time, Spartan meets this requirement, but it still requires a linear number of cryptographic operations. So in general, there is a trade-off between whether somebody wants to optimize for the prover time or they want to optimize for the proof sizes or verifier time. And the concrete performance that I've depicted here is for the case where there are a million R1CS constraints. So one natural question that we might wonder is if we can pick components from these schemes and combine them. For example, what happens if we pick an IOP from Spartan and combine with Supersonic's polynomial commitment scheme? The resulting SNARK would have the prover time of supersonic, so it wouldn't exactly meet the requirement of a quark. Or we could also try taking Spartan's IOP and combine with Fractal's polynomial commitment scheme. Here, the proof sizes and prover time of the resulting SNARK would be similar to that of Fractal, so it doesn't quite meet our requirement. Does somebody have a question?
Oh, sorry, that was just me, Srinath. I was Dara just joined, and I said feel free and ask questions throughout.
Thanks. So it turns out that if we just pick existing components in these existing schemes and then try to combine them in different ways, we don't quite meet the requirement that I described earlier in the talk. So it's also unclear how to reduce this pre-processing time a priori. Because all of them sort of require looking at the description of the circuit and doing some number of cryptographic operations for each gate in the circuit. So our scheme, Xiphos, is the first quadruple efficient transparent zkSNARK, and it supports R1CS. And it has this efficiency features. It performs a linear number of cryptographic operations. It produces logarithmic sized proofs. Verification time is also logarithmic, and the verifier's pre-processing time is a linear number of finite field operations. Crucially, there are no, the verifier's pre-processing involves only a logarithmic number of cryptographic operations. And in terms of concrete performance, it offers the fastest verification time. And in terms of proof sizes, the proof sizes are competitive with Supersonic's proof sizes, which offered the prior shortest transparent SNARKs. And the prover time is faster than every transparent SNARK, but it's about 3 to 4 times slower than Spartan, which offers the fastest SNARK prover, including SNARKs that might require a trusted setup. So there are actually, and it also offers the lowest pre-processing costs for the verifier. So to achieve this, there are 4 ingredients that we put together. So the first ingredient is the Spartan's polynomial IOP for R1CS. Then we combine this with Dory, and there are 2 variants of Dory. One is the Dory, the Dory polynomial commitment scheme that works with dense polynomials. And then we also transform the scheme to handle sparse polynomials efficiently using a compiler that we call Spark. And I would say that this is the most important ingredient in this entire composition. And we also have a technique that allows the verifier to delegate pre-processing work to some untrusted entity, which we call an assistant. And it turns out that this technique applies to any other zkSNARKs, so any other transparent zkSNARKs that we know of. So I think this technique itself is general on its own. There are also some other techniques that are in the paper that I'm not going to go into details of. These reduce concrete costs. This includes things like folding polynomial evaluation proofs. For example, in Spartan's IOP, the prover needs to prove about 4 polynomials. So it's going to fold all those polynomial evaluation proofs into a single polynomial evaluation proof. And there is also a more efficient zk transform that we discuss in the paper. So one question that people might ask is like, why one should build on Spartan's polynomial IOP? Why not use other IOPs that exist, for example, Plonk or Marlin? That's possible. In fact, it would actually reduce Xiphos's proof size by constant factors. I think it's about a factor of 2. But it also brings additional costs. For example, if you build on Plonk or Marlin's IOP, it would require FFTs, and this introduces an asymptotically higher cost. And it's also, in general, I think, hard to parallelize compared to parallelizing a multi-exponentiation. So in the
Yeah,
next,
but what if you you use say Plonk IOP, but you do like in the last part you do a sum check, right? In the part where you have to instead of computing the quotient, you reduce it to a randomized sum check. So could you still get the 2x and not have the FFT?
I think yeah, that's a good question. So at least the univariate, you're talking about using the univariate sum check, right?
Oh, right. So you don't have, yeah, we don't have a univariate sum check without FFT, which is a great open question. So yeah, cool.
Yeah. I think there is some work. I haven't thought about whether it's possible to use that directly in this context. There is some work that I think by Brian Pano and students that try to avoid FFTs.
Oh, is that published already? Because
yeah, there is an ePrint. I can maybe send you offline.
Oh, excellent. Thanks.
Yeah, it's possible there is a way to combine that IOP, but we haven't looked at that. Okay. So in the next part of this talk, I'm going to just go over these 4 different components that I've depicted here. Okay. So the first component that I'm going to describe is Spartan's polynomial IOP, and I'm first going to show a very simple description, and then I'm going to unpack this. So at a very high level, the Spartan's polynomial IOP is quite simple. It can actually be depicted with 3 steps. In the first step, the prover. Actually, before I describe this polynomial IOP, the problem that we are interested in is given 3 matrices ABC, the prover wants to prove the knowledge of C such that this relationship depicted on the slide holds, and this is the standard R1CS relationship. So to do this, the prover would just send a polynomial that encodes Z, and then the prover and the verifier would run the sum check protocol. I'll come back what this actually means, and it runs the sum check protocol on a very specific polynomial that's on the slide. I'll explain why the polynomial looks like this in the next few slides. And then the verifier makes 1 query each to 4 of those polynomials. 3 polynomials depend on the description of the statement, and 1 depends on the prover's witness. That's it. And it does some local computation using these queries, and then accepts the proof if those checks pass. And to compile this to SNARKs, in the first step, the prover sends some polynomial. Instead of that, the prover would just send a polynomial commitment using a polynomial commitment scheme. And then in the last step, when we make queries to the polynomials, the prover would send evaluations of those polynomials along with the proofs. And then finally, this entire protocol is public coin, so it can be made non-interactive using the Fiat-Shamir transform. And it's that simple. But the crux of this construction is why this equation looks the way it is, and that's what I'm going to unpack next. A little more detail on R1CS. So we are given 3 M cross M matrices ABC, and the problem asks, does there exist a vector Z such that A times Z Hadamard with B times Z equals C times Z, where C is this entry-wise multiplication of vectors. And the high-level idea here is that we can view these matrices and vectors as functions. For example, the vector Z can be viewed as a function that maps some S-bit strings to elements of a finite field, where S is logarithmic in the dimension of the vector. And similarly, ABC can be viewed as a function in 2S bit elements to something that maps to a finite field element. Then once we view these as functions, we can actually construct multilinear polynomials out of these functions. What I mean by this is that there exists some polynomial. I'm going to denote these polynomials as with a tilde on top of the variable. So for example, z tilde of y would agree with z of y for all values of y over the Boolean hypercube. And similarly, there exist unique multilinear polynomials that match the underlying functions over the Boolean hypercube. So once we have these multilinear polynomials, there exists a special function that I denote here with f. And there is a unique property about this function, which is that the function evaluates to 0 if and only if the R1CS instance is satisfiable. And it's actually pretty easy to look at this equation and see why this is true. It's just checking each of the constraints in the original R1CS. It just multiplies those matrices, and then it checks if each constraint is satisfiable. So this we aren't quite done here, because we need an instance for which we can directly apply the sum-check protocol. So what we do is we take this f, and then we take evaluations of f and take a weighted sum with another polynomial that I denote here by e tilde. And there's a unique property about this sum, which is that except for a small soundness error over the choice of this tau, the sum is 0 if and only if f of x is 0 over the entire Boolean hypercube 0, 1 s. And E here is a unique multilinear polynomial that evaluates to 1 if the arguments are equal and 0 otherwise over the Boolean hypercube. So the reason we are actually interested in this particular sum is there is a code primitive that Spartan employs called the sum-check protocol. And it's an interactive proof system for sum-check instances of this form, where G is a multivariate polynomial in L variables, and T is some target value in the finite field. And the prover, and it's an interactive proof system where the prover can prove that this polynomial G sums to this target value over the Boolean hypercube. And in this protocol, there are L rounds, where L is the number of variables in the polynomial. And in each round, the prover sends one, the verifier sends one random field element to the prover. The prover responds with a short message, and the message is of size D, where D is the degree of the polynomial in any variable. And then in each round, we perform a small number of finite field operations. And at the end of the sum check, the verifier must evaluate this polynomial G at a random point where R is chosen by the verifier over the course of the protocol. So there are several advantages of using this sum check protocol as a core building block. One of them is it requires no trusted setup. Second, it's public coin. In each round, the verifier is just sampling a random field element and sending it. So it can be made non-interactive in the random oracle model. Finally, it turns out that for many polynomials, so for example, if G can be broken down into a set of multilinear polynomials, the prover can be implemented in linear time. By linear time, I mean the prover only uses a linear number of finite field operations during the entire protocol. There's one disadvantage, which I'm not depicted on the slide, which is that it requires a logarithmic number of rounds compared to something like the univariate sum-check protocol, which is just a single round. But the univariate sum-check protocol, at least the ones that I've seen, would also require the prover to run in superlinear time. So it would require something like n log n finite field operations rather than n finite field operations.
Well, I think sometimes maybe like the interesting question is, can you say for some constant number of variables, can you get, so yeah, univariate maybe is the hardest, but for some constant number of variables, can you get linear prover runtime, right? That we divide it into a cube of like length n to the 1 over d for some d, and we have d, you know, for constant d, and can you still get prover linear runtime? That's that's something I wonder.
Yeah, so you're saying D is constant. D is typically assumed to be constant here. So D is.
Oh, sorry, no, I used D for I meant the number of variables. So L. yeah, like can you do L is, I don't know, 3 or 5?
Yeah.
And so instead of 0, 1, you'll have like n to the 1 over L as the domain. And can you still get linear prover runtime? I think that's a really good, great question.
Yeah, I think that's a good question. So you're saying instead of looking at the Boolean hypercube, we look at a larger space and then make the number of variables. Yeah, I think actually I think the original sumcheck protocol was actually not described over the Boolean hypercube. In fact, it uses H, which is a subspace that can be arbitrary. I think I haven't looked at whether it reduces. It can all these the linear time results can be applied in that context. I think it's an interesting question. Yeah, I think there is some properties of the multilinear polynomial that gets exploited in this particular construction, but you're right. That's an interesting question to look at. That can greatly reduce the rounds, which in turn reduces the proof sizes. So now if I come back to the slide that I depicted earlier, this equation is essentially checking, this equation on the second bullet is the sum check instance that I just unpacked. So in the first step, the prover assigns a polynomial, and then the core of the protocol is running the sum check protocol using this polynomial that we devised. And then in the end, the verifier just queries 4 of those polynomials at one location each. So a core, so if once we have this polynomial IOP, so to get a SNARK, we need a polynomial commitment scheme. So in Xiphos, the polynomial commitment scheme that we use is Dory. So here is one slide that I made on Dory. And I personally think this is a breakthrough result in the space of polynomial commitment schemes. And I've compared Dory's asymptotics and concrete costs with 2 other schemes, 2 other transparent polynomial commitment schemes. One of them is the polynomial commitment scheme called the scheme that's in Hyrax, which is also used in Spartan. And then the second row depicts cost under Supersonic's polynomial commitment scheme called DARK. And I've taken 5 different metrics that are normally considered for a polynomial commitment scheme. I think there are a couple of key takeaways here, which is Dory has better asymptotics than Dark, and with significantly better concrete performance on almost all of the aspects. Second, Dory also has better asymptotics than Hyrax's polynomial commitment scheme, and it outperforms that scheme even at small polynomial sizes. For example, so Dory's commitment time is slightly larger by a constant factor. But for example, if you look at the commitment size, it's constant sized. The prover time is a linear number of finite field operations in both Dory and Hyrax's polynomial commitment scheme. But as n increases, I think as n increases, the Dory paper shows that the prover time under Hyrax's polynomial commitment scheme and Dory approach the same value. Proof sizes are slightly larger under Dory than Hyrax's polynomial commitment scheme, because in Hyrax it uses bulletproof's commitment scheme, which has a very short, both are logarithmic, but there's a larger constant associated with Dory. But the verifier time, even though at least at n equals 2 to the 20, it's higher under Dory than Hyrax, but as n increases, Hyrax's polynomial commitment schemes costs increase pretty quickly. So I think at about n equals 2 to the 24, it completely outperforms Hyrax's polynomial commitment scheme on most of the aspects. But compared to Supersonic's polynomial commitment scheme, even at small polynomials, Dory outperforms on all aspects depicted here. So, so we can take this Dory polynomial commitment scheme and directly apply it to Spartan's IOP. It almost works, but there is one caveat, which is these ABC polynomials that I showed in the IOP are actually sparse polynomials. What I mean by this is that these ABC matrices are sparse matrices. So in practice, the number of non-zero entries in these matrices is linear in the matrix dimension, whereas the total number of entries in the matrix is quadratic. So if we directly apply Dory, it would incur quadratic costs for both creating commitments and producing evaluation proofs. what this means is that in the SNARK context, the prover would be quadratic in the statement size. So Spartan already had a solution to this problem. The solution is that is what we call the Spark compiler. So it takes an existing polynomial commitment scheme designed for multilinear polynomials, and it gives you a polynomial commitment scheme for sparse multilinear polynomials, and both the commitment time and the proving sparse evaluations are efficient. And there are two key techniques here. One is that it creates commitments to dense representations of sparse polynomials. So for example, if you are given a sparse polynomial in this matrix form, it creates three dense multilinear polynomials. We call row, col, val. And each of these polynomial is proportional to the number of non-zero entries. What they encode is that the row polynomial encode the indices, the row indices at which there are non-zero entries, and column polynomial encodes the column indices at which the non-zero entries appear in the original matrix, and the val polynomial encodes the coefficient in those non-zero entries. And then the second part of Spark is how to prove these sparse polynomial evaluations. And there are two aspects here. One is we devise an efficient polynomial IOP for proving sparse polynomial evaluations. And then we compile it to a SNARK using polynomial commitments. So to go into a little bit more detail on how we prove sparse polynomial evaluations, at a very high level, we express n-size sparse polynomial evaluations as a weighted inner product using these three dense multilinear polynomials, row, col, val. And it's given by this equation. So for example, if a tilde is the multilinear polynomial and we are evaluating it at Rx, Ry, so it's given by the weighted sum of these three components, E tilde evaluated at Rx, row of I, multiplied with E tilde of Ry evaluated at column of I, and then the weight for this inner, the inner product is given by val of I, and there are only n terms in this sum. And the core idea is that we can treat the first entry in this product as a memory lookup, where the memory is of size n, and it's initialized to evaluations of this E tilde of Rx, j for all j. So we can treat and we can also do the same for the second entry in the product. So we take the evaluations of E tilde at all possible points that somebody might want to query, and then create this memory. And to do this weighted sum, we just do n memory lookups for each of these tables, and then do a weighted sum. And one of the key techniques that we use here is that we transform this correctness of proving memory lookups to multi-set equality check using offline memory checking. And this is a technique from the early 90s that we used. And this particular technique was first used in the context of SNARKs for proving concurrent executions in a multi-writer database. And then in Spartan, we transform this multi-set equality check into proving grand product relations. And in Xiphos, we provide a special purpose SNARK for proving these grand product relations using Dory as the commitment scheme. And the main improvement here over Spartan is that it produces logarithmic size proofs instead of polylogarithmic size proofs. That was the case in Spartan. So finally, the fourth technique that I want to describe a little bit detail is how Xiphos outsources verifiers pre-processing work. So in Spartan, supersonic, or fractal, the verifier in a pre-processing step, it reads the R1CS instance or a circuit. It encodes the circuit into a set of polynomials. For example, in Spartan's case, it's a set of multilinear polynomials. And then finally, the verifier would create commitments to these polynomials using some public parameters. Whereas in Xiphos, we introduced the notion of an untrusted assistant. So this untrusted assistant could be played by anyone, including the prover. So in Xiphos, in a pre-processing step, the assistant and the verifier would just read and encode this instance into a set of polynomials. And then the assistant would send to the assistant would actually just only the assistant would execute the commit operation and sends those commitments to the verifier. The verifier then sends to the assistant a random challenge. Assistant then replies to the verifier with an evaluation of those committed polynomials at the challenge point chosen by the verifier. And then the verifier evaluates the original polynomials at the random challenge point and checks if the evaluation matches the prover's claimed evaluation, along with checking the evaluation proof provided by the prover, the assistant. And the upshot here is that the untrusted assistant creates cryptographic commitments, which is the most expensive part. And the verifier's cost is linear number of finite field operations and the cost to verify the polynomial evaluation proof, which is just a logarithmic number of cryptographic operations. And we think this technique applies to most of the other universal SNARKs out there to reduce pre-processing cost to the verifier.
So sorry, so could you remind, so what is the verifier pre-processing cost in the supersonic?
I think it requires linear number of cryptographic operations to create commitments to the polynomials.
Oh, and you're saying here it's a linear number of field operations.
Yes.
Okay, cool.
Because the assistant actually creates those commitments, and then the verifier's job is just to verify polynomial evaluation proofs and evaluate the polynomial at one point.
I guess if you were using this for something like a smart contract, then whoever is preparing the contract would act as the assistant. Yeah, that makes sense. Okay.
So we implemented all of these techniques by extending Spartan. And here is one slide that depicts the performance at a million R1CS constraints. And the depicted performance is on a single CPU core. And I think all of the schemes can be parallelized to reduce this prover time. But this comparison is still fair because all of them are run with one CPU core. There are a couple of key takeaways here, which is Xiphos's prover is fast, but it's not the fastest. The primary difference between Xiphos and Spartan, which gives you the fastest prover, is the difference in performance between BLS 12381's G1 and Restritor 255, because Xiphos requires Dory, uses Dory, and Dory in turn requires a pairing-friendly curve. But Xiphos is faster than all other SNARKs depicted here. Xiphos offers the fastest verifier. Xiphos's proof sizes are competitive with supersonic. Kopis, which is a small variant of Xiphos, shortens Xiphos's proofs, but it requires a slower verifier, both asymptotically and concretely. And the technique that I described for speeding up the verifier's pre-processing cost reduces pre-processing time significantly.
The ratio between the Xiphos and Spartan prover times there is a little bit larger than I would expect for the difference between Restritor 255 and BLS 12381. How was the arithmetic for BLS 12381 optimized? Because it looks like a factor of 4 there, and I would expect something like 3 or less.
Yeah, so for BLS 12381, we used the Blasters library. For Restritor, we used Cur 25519 Dalek with SIMD optimization. So it's included,
Right.
and I don't believe BLS implementation uses SIMD instructions.
Okay, that probably explains it. Yeah, that makes sense.
Okay. Yeah, and to summarize, the Xiphos provides the first quadruple efficient, transparent zkSNARK, and in terms of concrete performance, it has a fast verifier, shorter proofs. Prover time is fast, but it's not the fastest. And with that, I can take additional questions.
What was the ratio of prover costs between, say, Spartan and Grot 16 again?
Yeah, sorry, I did not depict here, but I ran Grot 16 as implemented in libsnark with the BN256 curve. I think it's about 70 seconds or 75 seconds, if I remember correctly. So Spartan is a factor 2 faster.
Right, okay. Yeah, because the BN254 curve is, yeah, about the same size as Ristretto. Okay, Ristretto 255.
Wait, I thought you said Spartan uses Dory. Oh no, Xiphos uses Dory. Okay. You said something that you have you improved the grand product argument from log squared to log in prover time. Maybe you can say a few words about that.
Yeah, so the improvement was in proof sizes. So in the original grand product argument, so it used a layered sum check. So for example, if you have a vector of size n, at each step it would reduce it to a vector of size n divided by 2, and it goes all the way to 1. And then it uses the sum check protocol repeatedly, recursively, to go from the output to the input. So you can think of it as applying the GKR protocol for the specific relation. And at each step, the original protocol required logarithmic size proof. So overall, it takes log square size proofs. So in Xiphos, what we did was we created a single sum check instance that can prove the grand product relation. So what we do is we take the original vector and then extend it with all the intermediate products. I think this is something similar to what happens in Planck. So you have the n-sized vector. So we augment this with another n-sized vector that carries all the intermediate products. And then we have a single sum check that checks this product relation across the entire vector at once. And because we apply a single sum check, it has just log n costs in terms of proof sizes.
Yeah, right. So if you do it it's multivariate. So you need to right in Planck, there's a simple generator that gets you to the next point for the multivariate thing, right? So you need something that gets you to the next, that goes over all the cube. I'm guessing, right? So yeah, something. What is this thing that? How does it look like in the multivariate case? This thing that gets you to each time to the next point.
Yeah. So actually, we don't do the next. So we have a special polynomial that essentially checks one product at a time. So we have a polynomial that essentially computes a product of 2 entries in the vector and compares it with another entry on the second half. So there is a polynomial that picks one of the entries in the second half of the vector and 2 entries in the first half, and then checks if the first entry is the product of the 2 entries. And there are n such checks that need to happen, and we just combine all of them into a single check by using the sum check protocol.
So okay. Yeah, go ahead.
Yeah, you can think of, for example, let's say somebody gave you an n-sized vector, and then we recursively computed the grand product, and we recorded the trace of this computation in the second half of the vector. There exists a polynomial that can actually check the computation that was performed by the original circuit with n checks on this 2 n-sized vector. And then we can check this relationship over the Boolean hypercube by just using some standard tricks that I depicted in one of the earlier slides using this E tilde polynomial.
So yeah, you're saying it sounds like if in the univariate Planck, you sort of accumulate the grand product just one element at a time. Here, it's more like a tree. Yeah, and maybe that's more convenient for the multivariate case.
Yes. Yeah, and it also does not require multiplicative subgroups, for instance. It works over any finite field.
So you can do it. You can do a grand product over just any set like h to the n, where h doesn't need to have any special structure.
Yeah, although we rely on the Boolean hypercube, so you're given a vector of finite field elements. We just treat that as a polynomial evaluated over the Boolean hypercube, and then we compute the product.
I'm just looking at the performance figures for Laconia in the paper. They seem quite impressive.
Yes, so Laconia, sorry, I did not depict this on the slide. So Laconia is similar to Xiphos, except it does not have the prove evaluations of A tilde, B tilde, and C tilde. So the verifier is evaluating those three polynomials. It's in analogous to bulletproofs, where the verifier is reading the circuit and computing with the description of the circuit.
So would it be possible to have a hybrid where you have an assistant that expands a Laconia proof, and then the verifier has to process a larger proof, but it's less expensive?
Is there one one instance or multiple instances in this case?
Either. Let's assume that we have a fixed circuit.
Yeah, I think if there is only one instance, I think if anyone tries to assist this verifier by proving ABC evaluations, it would sort of look like Xiphos. Because that entity would incur the cost of proving evaluations of these sparse polynomials. So the cost would go from whatever we depict for Laconia to Xiphos. But it's possible to amortize that cost. For example, if the verifier is evaluating or verifying a proof for the same circuit multiple times, so this cost, I guess in some sense, it's sort of like Sonic's help mode.
Right.
So the prover could just prove it once, and the verifier, the cost of the prover would get also amortized across n instances.
Okay, thank you.
Awesome. Yeah, thanks, Srinath. So I actually have a question on a slightly different theme that I think may be interesting to folks who are viewing this video, with that are maybe more kind of have general knowledge, but maybe not as specific knowledge as some of the prior questions that have been asked. And so my question is on the topic of basically the future of SNARKs in an era where quantum computers become a reality. And I encourage, by the way, everybody, all the smart people in this in the chat here to chime in. But obviously, SNARKs rely on cryptographic assumptions that may or may not hold, well, likely will not hold in the world of quantum computers, whereas STARKs seemingly, for example, STARKs and other schemes, will potentially hold in that world. And so I'm curious, Srinath, just from your perspective as a researcher in the space, how much does it make sense to push these forward, especially in light of the fact that SNARKs are very efficient compared to those other schemes I mentioned? But I guess how much does it make sense to push it forward without considering the potential world in which they may or may not actually be secure?
Yeah, I think if you're worried about post-quantum security, I think some of this work could still be relevant, because there are two, as I mentioned, there are two components here. One is the IOP, which is information theoretically secure, so it's secure against quantum computers, and then there's this polynomial commitment scheme. There are ways to make a polynomial commitment scheme out of protocols like FRI or even Ligero polynomial commitment scheme that you can combine with this IOP to get a post-quantum secure SNARK. I think maybe this modular approach of investigating most efficient IOP and most efficient polynomial commitment scheme, because all the cryptographic assumptions are inherited from the polynomial commitment scheme. So if one desires a post-quantum secure SNARK, they could use a post-quantum secure polynomial commitment scheme. I think this modular approach, I think, still has value to even in the post-quantum world.
Yep, I was going to say the same thing. That's my opinion as well.
Awesome. Yeah, thank you both. I know it's a question that a lot of people have, honestly, when they first come into this space and they kind of get an overview of the landscape. And obviously the question I had was based on kind of the simplistic understanding, but thank you guys for kind of shedding some more light on your views.
Yeah, I mean, as Srinath says, part of the work is reusable, and people can work on the polynomial commitment side and the IOP side independently, which is great. And I think actually, so things like Fractal are already practical for some applications, so it's definitely worth considering them, deploying them. Does anyone know if Fractal has been deployed in any real-world protocol?
Not that I know of.
Okay. I mean, I know SNARKs are being deployed, but go on.
I don't know if Fractal has been deployed, but I just wanted to comment that all these constructions that don't rely on only hash functions help us post-quantum researchers try to find the right mathematical tools. And so maybe we can find a post-quantum translation of pairings, something that works even against quantum computers. So yes, it's definitely worthwhile continuing this line of thought.
That's interesting. I'd kind of assumed that pairings were too structured in a sense to admit a post-quantum solution, but I could be completely wrong there.
Well, as soon as you have a group, then you can use Schwarz order finding algorithm to break
exactly.
It.
But doesn't
pairing that doesn't come with a group structure.
Huh. I thought that that a bilinear map kind of implied a group, but maybe there's a way to relax.
Well, in the same sense that you can do Diffie-Hellman with only group actions, you don't need a proper group for it. And so the object that your group actions are acting on is not itself a group. And so maybe there's a way to lift this to pairings whereby you can combine that object once but not twice. And then you would have a group action that supports one pairing but not two pairing computations.
Oh, I see. Okay, and that might be sufficient.
Well, I think maybe, right, this stuff, I don't know it well, but that Craig Gentry started with based on lattices, maybe it's sort of like a group, but that the addition is not always defined. Because sort of he does these operations on noisy vectors from lattices, and then the addition result is remove the noise to find the closest lattice point. But if the noise is too large, then you won't find a point. So maybe it sort of corresponds to a error group with error where the addition of some elements is not defined. Maybe something like that would be easier to do that's quantum resistant.
If your group axioms hold with only 1 minus epsilon probability that you are computationally speaking still a group, but it might be enough to break Schwarz algorithm. And so if that were possible, you could recycle all of group-based cryptography because it works in practice, and it only destroys Schwarz algorithm.
Do we know that Schwarz algorithm is the only quantum approach to breaking this kind of structure, though? I mean, for Grover's algorithm, we have, I think, a proof of optimality in a black box model, but don't think we have any similar proof for Schwarz algorithm.
Not to my knowledge, and there are definitely other hard problems which you might or might not be able to use for cryptography, but computationally hard problems out there where the best known quantum computer is exponentially more powerful than the best known classical algorithm. And I think you can characterize Schwarz algorithm as a special case of that, but I don't know the details.
I mean, I may be biased here, having developed a hash-based post-quantum signature scheme, but I tend to think that the most trustworthy post-quantum algorithms are the hash-based ones.
Awesome. Well, yeah, thanks everyone. It's a fascinating conversation. So thanks a lot for weighing in. I'm sure other folks on the channel as well as the YouTube channel will appreciate that insight. Are there any other questions for Srinath on the topic of quarks?
So what's the next step? What are the open problems that we should look at?
Yeah, at least here, I think the proof size, as you can see, it's still large. I don't know if there's ways to make it shorter. I think supporting maybe more custom gates in this model, that's possible. I think it is possible, but I guess it hasn't been explored. Of course, making the prover as fast as possible is another, I guess, question, because it's not the fastest as depicted here.
Yeah, I think maybe supporting lookups would be as useful as custom gates, and maybe that's simpler.
Yeah, lookups are somewhat supported already in the sense, for example, our grand product argument or the sparse polynomial evaluation relies on a memory lookup. I think the same approach could be exposed to the programmer, where it exposes this operation, and then inside the proof system, it's proven using the special purpose memory checking algorithm. But it hasn't been fully explored.
Yeah, I think R1CS plus lookups is an underexplored way of writing circuits, and would be a very nice model.
Yeah, we had some work that that still required. So this was the SAGL 18 that I depicted earlier in one of the slides, where we use multiset hash function. So it still required encoding a public hash function, so there are no secrets. But using a randomized version, which is what we do in Spartan and Xiphos, it does not require really representing a multiset hash function. It's just a fingerprinting function. Which is sufficient for lookups, could be exposed to the programmer.
So if I understand correctly, both Xiphos and Kopis require pairings, and if you want to do recursion in the straightforward way, that means an MNT4, MNT6 cycle. Is there any way to do it using just a half pairing cycle?
Yeah, that's a good question. I think it is possible so for example, what Nova calls folding, or what's called as accumulation scheme. I think the same applies here, because the commitments are elements of GT. You can accumulate them by doing one operation in GT. So I think half pairing might be sufficient, but I'll have to think more to say or confirm that.
Yeah, definitely worth exploring.
Okay, I would just mention, sort of going to that sort of, because ultimately we're building on top of Dory here, and Dory batches very efficiently. Sort of almost everything you have to do is GT arithmetic, and then you have to do sort of 4 pairings at the end. But if you want to batch, if you want to defer a lot of that computation, you can. And it may be the case that you can efficiently use pairing cycles to clean that up quite substantially.
Awesome.
If anyone wants to use HalfHerring cycles, by the way, I should probably plug the HalfHerring cycle that I generated, Pluto Eris, which is a 448-bit cycle with 1 BN curve. And that has some nice engineering properties.
Thanks.
Awesome. Any other questions for Srinath or Srinath? Anything you'd like to close with, or concluding comments?
No, thanks everyone for all the great questions. Thanks for inviting me to speak here.
Yeah, thank you.